Hey everyone, and welcome to this explainer. Today, we are embarking on an adventure I like to call the data detective's journey. You see, data is absolutely everywhere around us, and learning to read the hidden stories inside all those numbers, well, it's pretty much a superpower. And today, we're going to learn exactly how to uncover those stories.
But before we dive into the investigation, we've got to know the language, right? Think of this as our notation code breaker. Keep these mathematical tools handy. First, x represents our independent variable. That's the thing we're testing, inputting, or observing. Then we have y, our dependent variable, which is the outcome we're measuring based on x. Next up is n, which stands for our sample size, basically the total number of observations in our data pool. And finally, r is the sample correlation coefficient. It's a special number we'll use to decode exactly how strongly our variables are linked together.
So here is the roadmap for our investigation today. We'll start with sampling and bias, then visualize spread and variation. Next, we'll use two-way tables, graph scatter plots, learn exactly why correlation isn't causation, and finally, look beyond straight lines to exponential modeling.
Okay, let's jump right into Section 1, Sampling, Bias, and Data, gathering our evidence. Every good detective investigation has to start with solid facts. So how do we actually get fair data from the real world?
Let's do a quick pause check. Imagine a local radio station wants to know if their 20,000 listeners prefer music or talk shows. If they survey 200 people at a live music concert, is that a representative sample? Take a quick second to think about that.
The answer is a resounding no. Surveying people at a music concert creates a massive sampling bias toward music. Statisticians actually call this a convenience sample. I mean, sure, it's super easy to just ask the people who are already standing right in front of you at a concert, but doing that completely leaves out the viewpoints of folks who might be sitting at home listening to a talk show. If our sample isn't carefully selected to represent the whole population, it literally ruins our investigation before it even starts.
All right, moving right along to Section 2, Spread and Variation, Visualizing the Data. Once we actually have our hands on fair, unbiased data, how do we figure out what it's doing? Well, variation simply measures how our data values spread out from the center, or the mean. Standard deviation is absolutely crucial here. It acts kind of like a magnifying glass, showing us the average distance of all our data points from that mean. A small standard deviation means the data's bunched up really closely together, while a large one means it's spread way out. We also use box plots to visualize this. They show us the interquartile range, or IQR, which highlights exactly where the middle 50% of our data is concentrated. Plus, those little whiskers on the ends help us easily spot extreme, unusual values that fall completely outside the norm.
Let's see how all this builds in Section 3, Two-way tables, comparing categories. What happens when we aren't just looking at a single list of numbers, but we actually want to compare different types of data? Let's explore a contingency table, which is often called a two-way table. Here we are comparing two completely separate categorical variables, whether a driver is a cell phone user and whether they had a speeding violation in the last year. By just walking through the row and column totals, relationships really start to jump out. Out of a total sample size of 755 people in the bottom right, we can easily see in that bottom row that 70 total people had a speeding violation. But if we want to know how many of those 70 were also using a cell phone, the intersection in the table shows us it's exactly 25. Two-way tables organize our data perfectly, so we can start spotting these relationships and calculating the real probability of them happening.
Okay, moving on to Section 4, Scatter Plots, Predicting Outcomes. This is where we're going to take a fully worked example to see how we can actually forecast the future. Here we are pairing an independent variable with a dependent variable using real numbers. Take Amelia's basketball data, for example. She really wants to improve her game, so she tracked X, the hours she spends practicing her jump shot each week, alongside Y, the points she scores in her actual games. And wow, there is a clear trend here. As X increases from 5 to 12 hours, Y climbs from 15 all the way up to 36 points. To truly analyze this data, we just follow a simple step-by-step process. Step 1, we plot those XY data points on a coordinate grid to create our scatter plot. Step 2, we observe the overall pattern. For Amelia, there's a very clear positive association, meaning as practice goes up, points go up, and the dots form this overall linear or straight line pattern. Step 3, we draw a line of best fit. Using a process called linear regression, we draw a line that cuts perfectly right through the center of our data points. This is incredibly powerful, because this line now allows us to predict Y from any given X. If Amelia wants to score 40 points in a future game, we can use that exact line to predict how many hours she needs to practice.
But hold on a second. This brings us to Section 5, and perhaps the most important rule in all of data analysis. Correlation does not equal causation, the golden rule. We've got a predictive model now, but we need to put our detective hats back on and ask, just how reliable is this relationship?
Time for pause check number 2. Let's say our sample correlation coefficient, R, shows a very strong, statistically significant relationship between practice and points. Does practicing jump shots strictly cause more points to go on the scoreboard? Pause and think about it.
If you said yes, be incredibly careful. I want you to remember this phrase forever. Correlation does not prove causation. Just because two variables move together in a line, it absolutely does not mean that one is directly making the other happen.
So the absolutely crucial takeaway is this. The correlation coefficient, R, is a fantastic mathematical tool. It tells us the strength and the direction of the linear relationship in our sample. It tells us if those dots are tightly packed around our line of best fit, or if they're loosely scattered all over the place. We can even check R against critical values to decide if our sample is strong enough to model the entire population, but R never ever proves cause. Think about it. Maybe Amelia's practice hours went up simply because she was getting more sleep and feeling healthier. That extra energy might be the hidden variable that actually caused her to score more points during the fast-paced game. Our line models the relationship beautifully, but as data detectives, we can never claim that the math proves causation.
Finally, let's wrap things up with Section 6, exponential modeling, curved patterns. Because let's face it, the real world is incredibly complex, and sometimes our data just doesn't fit neatly into a straight line.
When we compare these two patterns, the differences are pretty striking. Linear patterns, like Amelia's basketball practice, fit a straight line with a constant rate of change. You add 2 hours of practice, you add a steady number of points. But exponential patterns, they form a curve. They represent rapid growth or decay, modeled by equations with exponents, like y equals a times b to the power of x. Think of things like populations multiplying, or how quickly a viral video spreads like wildfire online. The growth starts off slow, but then it rapidly bends and shoots straight upward. These kinds of real-world phenomena require curved, exponential models to tell the true story of the data.
Wow, we have covered a ton of ground today. Let's do a super quick data detectives recap of the 6-step process we just uncovered. 1. Collect your data fairly to avoid sampling bias. 2. Explore the variation and spread using standard deviation and box plots. 3. Categorize your data using two-way tables. 4. Relate those numerical variables using scatter plots and a line of best fit. 5. Check the strength of that linear relationship with the correlation coefficient R, while always remembering that correlation does not equal causation. And 6. Realize that sometimes you need to model complex realities exponentially. To wrap things up, I'm going to leave you with one final transfer question to spark your curiosity. If you went out and collected data on hours spent studying versus final grades, how would you test if a linear model is appropriate? Completely without assuming that studying literally caused the grade. Think about how you would map that out using the toolkit we just learned today. Thank you so much for joining me on this explainer, and remember, always look closely for the true story hidden in the numbers.